Hi, everyone. So far, we've been using the p-value method for hypothesis testing. And we've also looked at the confidence interval method for hypothesis testing. Now, this is often taught first in stats books, especially the older ones, but we're going to save the oldest method for last, lesson 36, the traditional or classical method for hypothesis testing. And actually, we're going to need this in the next lesson when we do two-tailed tests that involve the chi-square distribution, which were not symmetric. Okay, how can we use critical values? Remember those things from confidence intervals to do hypothesis tests? Okay, in the olden days, before computers were in common use, and well before iPhones or cell phones or anything like that, before computers were in common use, people like me had to use statistical tables and the traditional or classical method of hypothesis testing. Well, you could use the p-value method, or well, I mean, basically, you need a statistical table for any of these methods, right? I mean, whether it's the traditional or classical method, or the p-value method, or the confidence interval method, you need some sort of statistical table. All right. So we're going to use, yeah, as I said, we'll use the method for some hypothesis tests, particularly two-tailed tests in lesson 37, where we lose symmetry for chi-square when we analyze sigma and sigma squared. All right. We're going to go back to the magician's coin because it kind of makes sense for us to use our very familiar examples in order to describe this new method. Really, it's the oldest method. All right. As in lesson 33, example 1, we want to test the claim that a magician's coin is fair at the 0.05 significance level. Okay, maybe start this. Now we could let P be the probability that the coin comes up heads. Here's the setup. A magician's coin is fair. That means P equals 1/2 or 0.5. That's the claim. This is the case of equality. Of course, it's the null. The alternative is then two-tailed, favors both lower values and greater values for P. Two-tailed test. Alpha is 0.05. We now gather sample data. The coin is flipped 100 times, and it comes up heads 51 times out of 100. And we've done this before, right? And just think about it. Folks, think about it. David says his coin is fair. The magician's coin is fair. You flip the coin yourself, you get heads 51 times out of 100. Do you think you're going to call David a liar? Well, think about it, right? Okay, the sample proportion, P hat. So what is our best guess for what P is based on the sample? X over N, 51 over 100, 0.5100. Verify that the normal approximations apply, NP and NQ. If P is a half, Q is a half, they're both at least 5. As before in lesson 33. And in fact, you might remember this result. If you work out the z-test statistic, right, it's a test for P, a probability, the z-test statistic is 0.20. 51 heads out of 100, we get a z-test statistic, a z-score of 0.20, which is very close to 0, okay? If we had gotten exactly 50 heads out of 100 flips, then we would have gotten z equals 0. Well, 51 heads is very close. This z-score is very close to 0. So basically, we know right now very little evidence against the null. Very little evidence. We're probably not going to call David a liar. And before we used the p-value method, where we found the probabilities in relevant tails. In this case, well, it's a two-tailed test. So yeah, it's a two-tailed test. So we'll do this whole jazz. Positive 0.2, negative 0.2. It was a huge, huge p-value. Huge. No way we're going to reject the null. No way it's less than alpha. Now, instead of the p-value method, we will use the traditional or classical method to make a decision about the null. And on an exam, I would tell you which method to use. Both methods, in fact, I may have you use multiple methods, maybe the confidence interval method. And both methods will yield the same decisions and conclusions. And the same for confidence intervals. Remember that confidence intervals can be applied for two-tailed tests, at least the way we've been doing it. Now, again, this is a two-tailed test because remember, the alternative favored both the left and right tails. It's a two-tailed test, so we need two critical values. Let's show the picture right now. Well, I'll pull this up. This is a two-tailed test, so we need two critical values. Here's the general picture over here. Here's the picture that's relevant in this case. Alpha is 0.05 in our example here. All right, so this is a two-tailed test, so we need two critical values. Okay, in general, it's z sub alpha over 2 and the opposite. Okay, in this case here, here's a key hint, okay? In this case here, in our hint, we're gonna see that if alpha is 0.05, right, that's broken up into halves symmetrically, 2.5% in the left tail, 2.5% in the right tail, we get 1.96 and negative 1.96. See, before, we grabbed the z-score and we ran with it, and we found probabilities based on z-scores, or their opposites, right? But now, we're doing it more like confidence intervals. Remember, we used critical values when we were developing confidence intervals, all right? So these should look familiar. 1.96 and negative 1.96, these trap 95% or 0.95 in the middle for z distribution. As I said, folks, 1.96, you might be thinking about this a lot. All right. These are the CVs that helped us with a 1 minus alpha confidence interval before. So we've seen critical values before, right? In this case, 1.96 and negative 1.96. What's new is the notion of a critical region, all right? So in this case, the z-scores, the z-values that are more extreme than these critical values in a tail sense, right? So the right tail over here, the left tail over here, okay, they make up the critical region. So the critical region shrink this again, all right, critical region. So the critical region okay, the critical region would correspond to both this left tail over here and this right tail over here. Actually, I should lower these a bit. The critical region is technically a set of z-scores. They're not probabilities. Okay, so I should do it like that, where I'm pointing to these z-scores. I'm pointing to these, I'll put the mustache here. Moved over. Yeah, okay. So remember, the critical region, this is a set of, in this case, z-scores. Later on, they can be t or chi-square. Here, a set of z-scores. All right, the z-scores that are less than negative 1.96, the z-scores that are greater than 1.96. Again, on the examples I give you, you're not going to get exactly the critical value. That's no fair. The probability of that happening is 0 anyway. Okay, so the z-values, the z-values that are more extreme than the critical values make up the critical region. They correspond to the left and right tails of the z number line, and these are the shaded regions. They correspond to the shaded regions, or more precisely, the pieces of the z number line that correspond to the shaded regions. These are the z-values that would be too unusual under the null for the null to survive. Think of the critical region as the danger zone or acid bath where the null dies. So remember that for the critical region, what's the deal? The null dies here. We reject the null. So these cutesy ideas I'm giving you involve when the null is rejected. If the p-value is low, the null must go away. We reject the null. Here, if the z-score based on our sample falls in the critical region, this danger zone, this acid bath, right? A danger zone or an acid bath. The critical region, I might call it a CR, right? Okay, it's like a danger zone or acid bath regarding the null. It's where the null tends to die. All right, the null dies there. If your sample z-score, if the test statistic falls in the critical region, in general, if a test statistic based on a sample, if the value falls in the critical region, then we reject the null. The null dies. Okay, that means the sample is too unusual for the null to hold up. It's like seeing 99 heads in 100 flips, and the null said, "Oh, the coin's fair." Yeah. That null goes in the acid bath. Okay. I just told you this decision rule, right? And by the way, this is the professional term, decision rule. The decision rule for a hypothesis test using the traditional or classical method. If the value of the test statistic, right now it's z-scores, if the value of the test statistic lies in the critical region, the danger zone or acid bath, then reject the null. If not, then don't. All right. So what's the deal with z equals 0.2? Well, right off the bat, I mean, you know that this z-score is very close to 0, okay? So for any reasonable value for alpha, then I don't think we're going to reject the null. But let's see it play out. Okay, so we basically know what's going to happen, but let's see this thing play out. It's like watching a predictable film. Okay, it's like watching an M. Night Shyamalan film, and you know the twist. We're going to reject the null. That's the twist. We're going to reject the... Wait, I'm sorry. No, we're not going to reject the null in this case. We're not going to reject the null. We kind of know. All right. Okay, test statistic is z equals 0.2. Remember, the critical region, the CR, I'll put that in red. Okay, so the critical region corresponds to this piece of the number line over here, the z number line, and also this piece over here. The critical region is in two pieces. Values for z less than this critical value, values for z greater than this critical value. Now, and bear in mind that we were able to do this even before we got our sample. I mean, we could have determined all this even before our sample. We know it's a two-tailed test. We're going to use z. Alpha is 0.05. But now, after we get our sample, we can now find the relevant test statistic, the relevant z-score is 0.20. Where's that? It's almost smack dab in the middle. It is safely in the safe zone. I'll put that in blue. This is the safe zone for the null. Oh yeah, this is very cushy. I mean, the null is being put on a nice comfy bed, being fed grapes and wine. Oh, the null's fine there. Come on. The null's saying the coin is fair. Okay, so let's say the coin, the head on the coin is thinking, oh gosh, am I fair? Am I fair? I hope I'm fair. All right, I flip the coin, 51 heads out of 100. That coin, that head can rest assured, yeah, I'm okay. The null is going to be safe. We're not going to reject the null. Nowhere near the danger zone or acid bath. We do not reject the null. That's a weak result. So I guess I should write this formally, right? The test statistic, which in this case was a z-score, is not in the critical region, which means the null is safe, not innocent, but the null is safe. Don't reject the null. Okay, we do not reject the null. We do not reject the null. Is that strong or weak? That's weak. There is insufficient evidence to say something. Now, the claim was that the coin is fair. The claim was the null, right? The magician's coin is fair. The claim was the null. So we put the null on trial, okay? And we're weighing evidence against that null claim. Because the null is a claim, we weigh evidence against that null claim. Putting the pieces together, there is insufficient evidence against the claim that the magician's coin is fair. And again, you think about it. David comes, sees you and says, this is my coin. I claim it's a fair coin. You flip the coin 100 times, comes up heads 51 times in the 100 flips. there's insufficient evidence against David's coin being fair. Okay. So if you're wondering, do I have sufficient evidence to call David a liar? No, I have insufficient evidence to call David a liar. 51 heads out of 100. That's very much in the safe zone. The coin may very well be fair. Next up, we're going to apply these ideas to lesson 37 when we do tests for sigma and sigma squared, population standard deviation, and variance. Next time.